All right, everyone, let's get started. Have you ever really stopped to think about the incredible journey a single molecule of oxygen takes just to power your body? Well, in this explainer, we're going to follow that exact path. Think of it as a high-stakes relay race, from the air all the way down into your cells. We breathe thousands of times a day, and we don't give it a second thought. But every single one of those breaths kicks off this complex physiological relay race. So the big question is, how does oxygen actually make it to the finish line to keep us alive? Let's break down the science behind the win.
So here's our game plan. We're going to start at the starting line with something called the oxygen cascade. Then we'll cover the first handoff into the blood, the main race with the hemoglobin shuttle, and the finish line where oxygen gets delivered to the tissues. And of course, we'll look at what happens when things go wrong.
Okay, first up, the starting line. The race begins the second you take a breath. But what's actually pushing that oxygen forward? Well, it's not gravity. It's actually a powerful drop in pressure that literally pulls oxygen downhill from the atmosphere right into our lungs.
This whole process has a name, the oxygen cascade. And this is a perfect way to picture it, like a descending staircase. Oxygen starts at the very highest step, out in the atmosphere, and with each stage of the journey, it takes a step down in pressure. That drop is the driving force.
So let's put some numbers to it. At the very top of that staircase, the partial pressure of oxygen in the dry air we breathe is sitting at about 160 millimeters of mercury. That's our starting point. The first step down happens almost instantly. The moment that air enters our airways, it gets warmed up and humidified. All that added water vapor actually dilutes the oxygen a bit, causing the pressure to drop down to around 150 millimeters of mercury. And here's the biggest step down. By the time the oxygen reaches the alveoli, those tiny little air sacs in our lungs, it mixes with the carbon dioxide that's leaving our blood. This drops the oxygen pressure to its new baseline of 100 millimeters of mercury. And it's this pressure that's going to push it into the blood. All right, now for the first really critical baton pass. Oxygen has made it to the alveoli, but now it has to make the leap from the lungs and get into the bloodstream. This whole leap is governed by something called Fick's law of diffusion. But for our purposes, it really just comes down to three key things. First, the push. You've got this huge 60 millimeter pressure difference just shoving the oxygen forward. Second, the doorway. The combined surface area of our alveoli is massive. We're talking about the size of a tennis court. And third, the wall it has to cross is unbelievably thin, which allows for a super fast transfer.
And this just shows you how ridiculously efficient the system is. In a healthy person, this whole handoff is perfusion limited. That's just a technical way of saying oxygen crosses the barrier so fast, the only thing slowing it down is how quickly the blood can flow past to pick it up. But in diseases like pulmonary fibrosis, the membrane gets thick and the process becomes diffusion limited. It creates a major bottleneck and the whole race slows way down.
So, oxygen has made the leap. It's in the blood. But it immediately faces a new and pretty major problem for the main leg of the race.
And here's the problem. Blood is mostly water, and oxygen is kind of like oil in water. It just doesn't dissolve well at all. There's no way it can travel the long distances to our tissues just by floating around in the plasma.
I mean, just look at this breakdown. Of all the oxygen carried in our arterial blood, a tiny 2% is actually dissolved in the plasma. So, where's the other 98%? Because let's be clear, that 2% is absolutely not going to cut it. It's nowhere near enough to power our muscles or our brain or anything vital. So how did evolution solve this massive delivery problem? Well, it came up with a specialized delivery truck, hemoglobin. The other 98% of oxygen basically hitches a ride by binding to hemoglobin molecules that are packed inside our red blood cells. And this is a game changer. It boosts the blood's total oxygen carrying capacity by about 70 times. Incredible. Okay, we've now reached the final and maybe the most elegant leg of the race. Getting that oxygen off the hemoglobin truck and delivering it right to the tissues that are working the hardest. You see, hemoglobin isn't just a dumb truck, it's a really smart delivery system. It actively responds to local signals. When it gets to a hard-working muscle, it senses the byproducts, more CO2, a lower, more acidic pH, and higher temperatures. These signals, what we call the Bohr effect, basically tell hemoglobin to change its shape and drop off its oxygen cargo right where it's needed most.
So this entire relay race is this beautifully tuned system, right?
But what happens when disease or toxins come along and just throw a wrench in the works and sabotage the whole thing?
Let's take anemia. You can think of this as showing up to the race with too few runners on your team. In this case, too little hemoglobin. So even if your lungs are working perfectly, you just don't have enough carrying capacity to deliver the oxygen your tissues need, and that leads to tissue hypoxia. Carbon monoxide poisoning is even more dangerous. It's basically an imposter molecule. It binds to the exact same spot on hemoglobin as oxygen, but it does so with 250 times the attraction. So not only does it steal the seat, it holds on so tight that it makes it harder for any other oxygen to be released. It completely hijacks the delivery trucks. And let's circle back to that first handoff. In diseases like pulmonary fibrosis or edema, that respiratory membrane, the track for oxygen's leap into the blood, it gets all thick and waterlogged. This slows oxygen's diffusion down to a crawl, and the blood might just pass right by without ever getting fully oxygenated. So at the end of the day, just getting oxygen into the blood really isn't the whole story. The real physiological magic is that incredibly intelligent system that makes sure oxygen gets delivered precisely where and exactly when it's needed most. It's not just about transport, it's about targeted, responsive delivery. And that's what's truly amazing.